Alright, so let's create a data source for Boston housing. Right? And we'll use advanced advisor. Okay, so let's make sure that everything is okay. So you should always check this and make sure that the roles and the levels are all right. So age is interval, binary, so you have interval. Okay, so and here we need to change cat medv to target and medv to target as well. Of course, when we run the model, we'll use only one of the two as our target. The other one we need to reject or not use. Okay. All right. So decision processing. So here is where we will go over this later on. But remember, when we have asymmetric costs on your decision, so this is where you will enter those costs. So if you click yes, then it will give you the default profiles, and then you can create prior probabilities, and then decisions is where you will put the cost. So cost of one decision is say -2 and 50 is what we used in the homework assignment, right? Cost of sending out is $2. So a monetary outcome is -2. The profit we make is 50. This is where you will enter that. Okay, but we'll do that later on. Oops. I exited out accidentally. All right, so okay, so we're not going to do decision processing. All right, no sample data, no some housing. So, all right. All right, so then bring Boston housing in. Okay, and we're going to partition the data into 40, 30, 30. So we're just going to keep the default proportions. And the reason why we are doing a test here is because validate is used in the process of selecting K. So when to make a proper comparison between this and other methodologies, you need a test data set that has not been used for any estimation purposes. Okay. Then the model here is MBR. So these are the parameters. We'll come to this in just a second, but before we proceed, there is one thing that we need to talk about, and that is the distance measure. Okay, so the distance formula that we looked at. Okay, so this is affected by the scale of the predictor variables. Okay, large values will have large contributions, okay, to the distance, and x variables whose values are small will have very small contribution to distance. So the x variable, the predictor variables whose scale is large will have undue influence on the distance measure. Okay. So we have to even things out, okay, to have the same playing field, and therefore it is normal to use some kind of transformation. Okay. And he also expects the predictor variables to be uncorrelated, so that's what is meant by orthogonal. Orthogonal means they are perpendicular to each other in terms of their orientation when you plot, and that is achieved through principal components. When you generate principal components, you get two things from it. The principal components are orthogonal, meaning that they are uncorrelated, and then they are all in the same neighborhood of scale. So you get both requirements achieved through principal components. So we bring in principal components. Okay. Now principal components. We use correlation. The scales are different, you use covariance if the scales are about the same. So we're going to use correlation so that the effect of scale is evened out. All right, and okay, so it's going to give us cumulative 99% of the variance. Okay, and then you connect MBR. Now MBR has, okay, so you can now go to variables. Okay, these are the parameters. So let's look at variables. So now the MED-V is automatically set to no, and cat MED-V is set to S. So it's going to be a classification K nearest neighbor, and then everything else is default, so it looks good. Okay, so you have to check that. Then the method, there are two methods available in SAS, RD-tree and scan. Scan, okay, remember what we have to do is that each record from the validate, so you have to make a classification for that record, right? So you have to take that record and compute the distance for that record from each of the records in the train set. You have to go however many records there are in the train set, you have to find the distance for all of them, and then based on the K value you make classification, and then you take the next record, repeat, the next record, repeat, which means this is computationally very, very intensive. So each record you'll have to go through and compute the distance, and if you have millions of records, this could be a long process. So that's what scan does. Scan doesn't do any optimization, it just goes through the entire data set, computes all the distances, and figures out the classification. Whereas RD-tree uses a more clever search methodology, so it breaks down the training set into groups and figures out distances within each group, so it's a little more efficient way for implementing the KNN method. So if you have large data set, then RD-tree is what you need to use. RD-tree is default. Okay. Scan would be more naive. Okay, just go and brute force everything included, and it can be quite inefficient, right? All right, so next is the number of neighbors. Okay, so this is where you specify how many nearest neighbors is retrieved. So right now it is set to 16. So it will look at 16 of them, the 16 nearest neighbors, and then do a polling with that 16 neighbors. All right. So let's go ahead and run. All right, so let's look at results. Okay. So here we have the fit statistics and the train classification data, and we have validate classification data. Yeah. And here is our false negative, true negative, false positive, true positive. Okay. All right. So let's go ahead and enter this piece of information here. So we have MB16. So false negative is 19. Okay. True negative is 127, and 6 is true positive. Okay, and 0 false positive. We'll look at these charts in a little bit. Okay. So let's now go back here and run another KNN. Okay. So copy this node and paste it. Right. Now we're going to use 8 as the number of neighbors. All right. Let's go ahead and rename these nodes. K equal to 8, and that one K equal to 16. Run that. Okay, results. Okay, once again, scroll down, and we have for the validate set, okay, 18, 125 to 7. 18, 125 to 7. Okay. Now we will look at these charts in a little bit. So right now we have charts only for train and validate, right? So this cumulative lift. So we have train and validate. What happened to test? Okay. So to get, you have to download test data ourselves, and then we have to generate some of these charts. But we can do one more thing. So we can do model comparison node, right, and connect these two, and then run model comparison. So that will give you the comparison including the test. Okay, so now look at the results. So then, so you have the ROC chart. One again, ROC chart is generated only by the comparison node. So if you want ROC chart, you have to add a comparison node, and if you have classification chart and the lift chart, okay, so we have so that is your test. Okay, so you have, that is the test. So if you scroll down, so you get train, validate, and then test. So you have to add that model comparison node to be able to generate those.